So in the last lecture, we just started talking about pointers to members, and particularly pointers to members for data members is really what's more important from the point of view of this course and the assignment that you're going to be doing that's using some of this stuff. So there's various ways that you can kind of conceptualize the notion of a pointer to member. But again, a pointer to member is just providing a way to identify a particular member, in this case, a data member of a class, but without tying it to any particular instance of an object of that class. And probably a good way to think about, in the case of data members, a good way to kind of conceptualize the notion of a pointer to member is to think of it as an offset from the beginning of the object to the place where the data member starts. Maybe I can illustrate this by way of a picture here. So, suppose we have some type, called widget, for example, and has a few data members. We have an int I, a float f, some other stuff, and then a char c. And then we have some kind of pointer which is pointing to the widget, which is called wp. So in terms of a picture, the pointer is going to point to basically the first address in memory where this particular object resides. The way to help conceptualize the idea of a pointer to member in the data member case, you can think of it as an offset from wp to where the data member starts. So for example, if I is the very first data member in the class, then most likely it's going to start at offset 0 from the beginning of the object. So the value that you can imagine or conceptualize as associated with the address of widget : I is like 0. It's an offset of 0 from the start of the widget. Whereas supposing, for example, that maybe ints are 4 bytes, so there's this I is going to take 4 bytes, and then this thing doesn't have any padding, it immediately follows right after the int. Then this would be offset 4 from the beginning of the widget object. And you can think of the address of this particular member as being that offset 4, for example. It doesn't actually have a numerical value, and this is only a conceptual thing. There's nothing in the language standard that says there has to be like numerical values associated with these pointers to members for the data member case. But it's a good way, I think, to think about it. And if you think about things this way, then it makes a lot more sense why pointers to members by themselves for data members are not a particularly useful thing, because all it is an offset from an actual, the beginning of a widget in this case. But if you don't know where the widget is in memory, in other words, if I don't tell you what WP is, then the pointer to member is useless, because it's saying go to where the object starts and then add this offset to it. But if you don't know where the object starts, you can't really do anything. So this is the reason why whenever you use a pointer to member, you always have to have some object to apply that pointer to member to. When you dereference it, you have to give an object for which you're going to dereference that pointer to member. And this applies whether it's a pointer to a member, to a data member, or a function member. It really makes no difference. Anyway, so hopefully that gives you some idea to help kind of visualize what these things actually are, these so-called pointers to members. So I have a simple code example at the bottom of this slide. We have a widget class here. It has 2 members, one which is a non-static data member and one which is a static data member. So the first one's called I, second one is J. They're both ints. And then down here we create some widgets, a widget called W, a widget called V. And then what we're going to do is we're going to take the address of a particular member. So this expression ampersand widget : I will yield a pointer to member. It's a pointer specifically to the I member of the widget class. So if we want to assign this to a pointer to member, the type of it, again, for simple types in the language, they read from right to left just to make things confusing instead of left to right. So like when you read this right to left, star means pointer. It's a pointer to a member of the widget class, and its type is int. So for example, down below here, we can take a class or an object of the widget class like W or V, and we can then take this pointer to member that we have up above here, that we call PTM, and we can dereference it. So what this is going to do, when we say w.star.ptm, what this is going to do, it goes to where the object W resides. When we dereference this pointer, it's just effectively going to add the offset that's associated with that member, and it's going to access whatever member that is. In this case, PTM refers to the I data member. So effectively, this w.star.ptm is equivalent to just writing w.i, because the pointer to member is basically just referring to the particular data member I. Again, this notion of offsets is just a conceptual thing. If you try to use a pointer to member as a numerical value, the compiler will not like you. It will say you're not allowed to do this. But in terms of the implementation underneath, a lot of compilers do actually implement things this way because it's kind of a sensible way to do things. So basically, this line here is going to just have the effect of setting w.i to 42. So in this widget here, the data member is going to be set to 42. And if we do the same thing for V, it's going to basically set, this is basically just going to be a nickname for v.i. In other words, when I dereference this pointer to member, it's going to be referencing the I member of the object v. And then this is just going to set it to 42. So then this widget here, the one called v, will have its data member I set to 42. The other thing I want to talk about here, if we take the J data member here, and J is a static data member. So static basically means that this particular data member only exists kind of class-wide. It's not stored in the individual objects. It's not on a per object basis. So if we take the address of this particular member, we just get a regular pointer. So this thing here is not a pointer to member. It's just a pointer to an int, because this thing doesn't actually live inside widget objects. There's just a single instance of it which applies to the whole class. So when we're talking about pointers to members, this is why it's always for non-static members. It's the members that are actually stored in each object of the class that we're talking about. Any questions? So I have a few examples here. The only one that I really want to go through is this new slide that I added. So this is one of the ones in the email that I sent out whenever it was, today, yesterday. It's all a blur to me. But anyway, this is on the course website. And what I want to give is just some kind of use case for using pointers to members without getting overly complicated. That gets left for the assignment. But try to keep things kind of simple, at least to begin with. So what I have on this particular slide is I have two classes, one called point, one called thing. So point has a couple of data members, a bunch of doubles, X and Y. And the thing has a couple of data members, I and F, which have in float type respectively. And what I want to do is I want to write a function which is called accumulate. And what it's going to do is I give it a range of elements, which are represented by these iterators first and last. So first and last correspond to a range. And it's going to be a range of some class type. So we have basically iterators that are referring to maybe like a bunch of points or a bunch of things. And what I want this function to do is it's going to sum up a particular data member of that class object. So it's going to loop over a whole bunch of objects of the same type, summing up one particular data member. And this is what this template parameter here, P, is doing. P is going to specify the particular data member via a pointer to member. So in other words, P is going to be a pointer to member. And pointer to members, by the way, are constant expressions. So you can use them in templates, like as template parameters. Because anything that you put into a template parameter has to be something that's known at compile time. But pointers to members are compile time constants. They're constant expressions. So we can do this. And when we do that, when we compute this sum, we're going to allow the user like the person who calls us, to specify an initial value of the sum, because maybe you're trying to accumulate a bunch of sums together. So maybe you don't want to start from 0. So this is just an extra parameter that we can specify here. And if you look at what the code's doing, it's not really doing too much fancy stuff. It's just looping from first to last, incrementing this iterator each time through the loop. And what we're doing is we're taking our initial sum that we were given and we keep adding to it each time through the loop. And the main point of this particular example is just this little bit of syntax here. Here we're using the pointer to member, which is passed in through P here. And we're going to dereference that particular member, and depending on which template parameter is passed in here for P, we could be accessing different data members of the class. And whichever one it is the one that's going to get added in the sum, and then at the end we just return the sum. And the type that's passed in for this parameter here, which is the type T, this is a template parameter, which is a type. The value that's being computed in here, when we're computing the sum here, the type of this sum variable is T. So the computation is going to be done with whatever type T is. So if T is an int, then the integer, we use integer arithmetic. If T is like a float, for example, use float arithmetic. If it's a double, use double arithmetic, and so on. This is important because you might want to, you might care about whether things are being done with floating point arithmetic or integer arithmetic, and so on, depending on what types are involved. And then the return type, of course, is just a T. It matches whatever the sum was here. If we look at the code down below that's using it, so we have this array of points called P, which has 3 points in it, and we have this array of things called T, which has 3 things in it. And then what we want to do is we want to just compute a sum of the data members, each of the data members for each of these types. So for example, I want to iterate over all the elements in this array P, a whole bunch of points here, 3 points. So I'm going to iterate from the beginning of the array to the end of the array. And the initial value that I want to use for the accumulation is 0. I want to start from 0 in all these cases. In this particular case, because the things that I'm summing up here, I'm going to be summing up the X data member. If I look at the type of the X data member, it's a double. So probably I want to use a double for this parameter here. So it's 0.0. If you remember, 0.0 is a literal, specifically of type double. So the accumulation is going to be done with double arithmetic. So when this function is called, basically we're going to sum up like the value 1.0 plus 0.5 plus 0.5, and then that's going to be returned from this function here, and we're just basically printing it out. We can also invoke the same template function, but in this case, we're giving it a different pointer to member. We're giving it the pointer to member for y, and again, we're looping over the whole array, and this is just going to sum up all the y values. So the y value is the second data member and the second member in the class, so it's going to basically be summing up 21 plus 21 plus 0. So we get 42. And then we do a similar thing using the array T here. So here we have an array of 3 things. And basically the first data member in this class is an int, and the second one's a float. So we have basically an int and then a float, an int and then a float, an int and a float. And in the first function call that we have here, we want to add up all of the first members, which are ints, the data member I. So the thing that we're passing to accumulate is pointer to member for I. So when we're running this loop here, the thing that's going to be getting added, the thing that we're going to be accessing is the I data member. And in this particular case, because the I data member has type int, probably when we're choosing like our initial value that which also will determine the type that's being used for the sum, we probably want to choose that as an int. And then in the last case here, we're trying to sum up the F data member. So we're going to be adding basically 0.1 plus 0.1 plus 0.1. In other words, the second data member, which is called F here. It has type float. So when we're doing this sum, probably we want to make sure that the sum is being done using arithmetic where the type involved is type float. So this is why we're using 0.0f here. So that when the type is deduced by the compiler for this type T here, because it's going to choose it basically to match this parameter, T would be deduced as float in this case. If, for example, we just wrote 0 here instead of 0.0f, the result we get probably isn't going to be what we expect. Because if I just write 0 here, then when the compiler deduces the type T, it's going to deduce this as int, which means that this variable init sum is an int. So when we're doing this accumulation, we're doing it with integers. So it doesn't matter if the right-hand side of this is something that's like a double or a float. All you're going to do is just keep rounding the result, because the accumulation is being done with an integer value. So the thing that's being returned is an integer, which is probably not what you wanted. So sometimes the type can matter a lot. Even like when you're using literals, sometimes the type of a literal can matter a lot, especially like in contexts like this. And is there anything else I want to say about this example? Oh, yes. A few other comments. When the compiler has to deduce these template parameters here, it can deduce it. There's some hope that it could deduce iter, and it could deduce the type T, because these types appear in the parameter list of the function. So iter appears for the first 2 parameters, and T appears in the last parameter to the function. But you'll notice that P doesn't appear anywhere in the parameter list here. So there's no way the compiler could ever deduce P, because the way that it deduces things is it looks at the way you're calling the function, it looks at the different types of the arguments that are being passed, and it uses them to deduce the types for the various parameters of the template. But because P doesn't appear anywhere in the parameter list here, there's no way that it can deduce P. And this is the reason why we're providing an explicit value for this template parameter. The remaining 2 parameters we don't bother to put in here because the compiler can deduce them. We could write them out if we wanted to be what the compiler would have deduced. In other words, we could add like a comma and then another parameter and a comma and then the third parameter. We could plug in values for the iterator type in T. But because the compiler can deduce them, we don't really want to do that. Just let the compiler do it. But in the case of the first template parameter P, the compiler can't deduce this, so we have to explicitly specify it. So this is the reason why we have the single template parameter for each of these function calls. And I think that covers everything I want to say for this example. Any questions? Yep.
So we do not do I arrow X here, because I not get like the arrow dereferences I to the object of type point in the first.
So if you replace this, like for example, this line here, I think you're talking about. So if I replace this with I arrow X, this function will work as long as what I want to sum up is the X member. But if I want to sum up anything else, I have to write a new function, right? So what this does is it gives you the flexibility that you can basically plug in the particular thing that you're summing. If you didn't need that flexibility, then this would be like overkill. You don't really need to do this. Yeah. This is effectively what you're doing here is you're kind of leaving the particular member as a thing to be filled in by the person who's calling. Any other questions? Yeah.
Does the array have to be const expert here?
This doesn't really matter in this context. I just made it const expert because, well, I probably would make it const because I have no intention of changing it. And it turns out that because the types are literal types, I can make it const expert as well. But there's not anything particular in the example that requires. I could just drop the const expert altogether. Everything will still work fine. Yeah. Any other questions? So So the next few slides I'm going to skip over. And what I really want to talk about is I'm going to revisit, we talked about much earlier in the course, a doubly linked list with a Sentinel node. This was back in maybe, I don't know, say the third lecture or something like that. And what I want to do is I want to revisit that particular container that we talked about earlier, but revisit in the context of an intrusive container. So what we looked at before was a non-intrusive version of this container, a non-intrusive doubly linked list. So what I want to do now is revisit in the context of intrusive containers and kind of contrast what we had before, what we end up with when we try to make things intrusive. And probably the best way to start to explain this initially is by looking, if I skip a few slides further ahead here, is actually look at the code that would be using this class, because this is maybe the first place where things really evidently become different compared to a non-intrusive container. So I have some kind of widget, which I want to basically create a container of widgets. And basically the way, and I have this list type here, which is our doubly linked list with a Sentinel node as the underlying implementation. In a non-intrusive case, you would just specify maybe widget and you're done. Like there's one template parameter, which is the type of the elements, and you're done. But with the intrusive case, we have this extra parameter here. So this is like the first difference that we notice, this extra parameter that we wouldn't have in a non-intrusive case. The other big difference we notice here is that we have this widget type, which is some type that we want to use. It's not really the containers type, it's like our thing. And we have this mysterious data member called listHook. Well, it has type listHook and it's called hook, appearing as a public member in our class. And this data here is not for the widget, it's not for us. We have to put it there in order to be able to use the container. If we don't put this there, the container code is not going to compile even, like it won't work. Because essentially what's happening is the list container type is going to rely on us to put the data members that are necessary for kind of helping to manage the container into our own data structure that we're going to put into the container. So if we back up to the previous slide and look at what this thing is here, this list hook is simply this data type at the top here. It's our next and previous pointers for the doubly linked list. So effectively what's happening with the intrusive container compared to the non-intrusive one, in a non-intrusive case, the next and previous links are hidden from us in the implementation of the container. We never see them, we don't have any way to access them, they're not in our actual type that we're putting in the container. Whereas in the intrusive case, what happens is the type that actually has the next and previous pointers, we have to put it into our type in order to be able to use the container in the first place. So this is a really fundamental kind of difference between these two approaches to doing things. And by doing this, this allows us to have certain flexibility that we wouldn't have in the case of a non-intrusive container, but there's also downsides, as you can imagine, because essentially we're leaking implementation details into the person using the container, because now they know, oh, there's a next and previous pointer, there's this thing called list hook and all this stuff. So there's downside to leaking information in this way. And yeah, I think that's all I want to say there. Yeah, in terms of a picture, what we have is something like this. So for the specific case where the particular things that we're putting into the container are widgets. So there's because we're using a Sentinel node, there's this dummy node that has no data associated with it. It's just a pair of next and previous pointers. The next points to the first element in the list and previous points to the last element, just like in the case of a non-intrusive container that we talked about before, which followed this kind of pattern. But the really key difference here is that if I maybe show the non-intrusive case first, so this is kind of warping to a completely different section of the lecture slides. But if I look at what we had before, this was the case that we talked about way back near the beginning of the course. The key difference here is in this particular case, for a non-intrusive container, the actual nodes in the list were some private type that you didn't have access to. You don't know what it's called. It's all hidden from you, the implementation details. And when you put elements into the container, what's happening, there's this hidden node type, and the hidden node type has as either a data member or a base class object, the actual element, the object that you want to put into the container. So this would correspond to our widget in the example that we were just looking at a moment ago. So in this case, you have like a node, and then contained within the node is the actual widget or like the type that you want to put into the container. If we go back to what we were just looking at a moment ago, in this particular case, we kind of turn things inside out. What we have in this case is now we have contained inside our type are the nodes that make up the list. The nodes are basically these hook members, the members that have the hook, what was it called, list hook type or whatever it was called. So this is like a very fundamental departure from what we had originally in the non-intrusive list. And then because of this, there's certain benefits that follow from this. There's also certain disadvantages as well. And we can implement the iterator just like we did in the case of a non-intrusive container. The iterator is just is referring to a particular node in the list. Maybe the only other thing I need to comment on, like the reason that data pointers to members become important, and particularly pointers to data members, is that we need some way to specify, like since we're providing to the container this type that we want to put into the container, and we're providing the data member that holds the next and previous pointers, there needs to be a way for us to tell the container, the particular data member I want you to use that has the data that you expect where the next and previous pointer should be, this is the member where you can find it. And you basically provide that information through a pointer to member. And maybe one other comment I should make is that if, for example, we have a pointer to one of these hooks, so maybe we're pointing at this particular node in our list. Again, the nodes in the list are basically these hooks, and we want to get a pointer to the widget. This is not something that can be done portably, but because most compilers implement pointers to members in terms of offsets, essentially what we can do is we can play some games here, and we can say, well, if we know which member is holding this hook, we can figure out that the difference between the address of this thing and the address of the widget that contains it is a fixed number that we know at compile time. And we can just back up by those many bytes and find the widget that corresponds to that hook. So effectively what we have here is, like, as far as the list is concerned, the only thing it really needs to deal with for the most part are just basically these nodes here. But every once in a while, you might want to access the data that's associated with a node, in which case you have to sort of take the pointer to the hook and sort of back up earlier in memory to where the widget starts and then access the widget, or more generally, whatever type you're putting into the container. Any questions? So I think probably a lot of these points I've probably already covered.
Sorry, does this mean that our data type has to support this sort of hook object?
Okay, maybe I should back up to, so like for example, if we look at this is kind of what the code would look like that's using the particular list type that we developed here, this intrusive list type here. Mm-hmm. So if you want to use, so for example, if I didn't put this hook here and I just tried to use this widget, like it's not just my widget without any corruption of other stuff that's related to implementation details of the container, if I try to do this, it's just going to fail to compile, because this code here is going to be trying to look into the widget object expecting that there's something where the next and previous pointers are, and they're not there. And what's going to happen probably be a compiler, because it's trying to access something there that's not there. So this is the kind of one of the downsides of using an intrusive container, is that the details of the container start to creep into your code, right? Because normally, in order to put a widget in a container, you wouldn't normally need to have some of the guts of the container in your widget. But this is what we have here. Part of the guts of the container, this list hook thing, is getting stuck into our class object. And without putting it there, we can't put it in the container. It's not going to work.
We could like subclass the original object though, and then add this field into it. And that way we can. Well,
there's kind of two ways that you can compose things or aggregate things. So like one way is you could have a data member and we could stick this in a data member. Another approach we could take is instead we could use an inheritance. So we could stick this thing into our widget class by inheriting from some kind of list hook type. So there's two ways to do it. I figured that well, the one I'm presenting is the one that relates to the assignment that you need to do. And I figured probably this approach is easier to understand than maybe dragging in some more complicated aspects of inheritance, because maybe not everyone might not be quite up to speed in terms of inheritance in C++. But you could do it that way. That's a good observation to make. And actually, some of the downsides of doing things with data members like we've done here go away if you use inheritance, but it just makes the code might be a little bit more difficult for people to code that way. Yeah. Any other questions? Mm-hmm.
Would it be true that if you made like the convention that you always make list hook the first data number, so then the offset that you were talking about would be 0, then would the widget to be able to access it have the same address as just the pointer to the list hook?
It wouldn't be kind of a very nice way to do things. Like you could maybe say, well, I'll just always make sure that this hook is at the beginning, and then effectively hard code into the code. It's assuming that it's right at the beginning of the data structure. But this is probably would not be a very desirable way to do things. I mean, you could maybe sort of make it work, but it would be very brittle. This just gives you a kind of a more powerful way to do things, because also you can do things like what's shown in the bottom code example, which I didn't really comment on. With intrusive containers, I mentioned before, one of the benefits is you can put objects in multiple containers at the same time. And the way this would work, for example, if I had a gadget, and I want to put gadgets in like 2 different containers, like 2 different doubly linked lists at the same time, I can do this because what I can do is I can have 2 of these list hooks in my class. And when I try to create a list of gadgets that's using the first hook, so it's using like the next and previous pointers in this member to kind of chain everything together, what I'll do is I'll use this type where the pointer to member I'm specifying is the one for the first hook. If I want to use like I have a list of gadgets where things are going to be ordered by this second hook, like I'm using the next and previous pointers that are stored inside this thing, that I can specify the second hook. And I could do this as many times as I want. I could have this thing in like 50 different containers at the same time if I wanted to. I just keep adding more and more members that are needed for the additional types of containers that I want to put this object into. So it's very, very flexible. And if you do things this way, it gets kind of harder to try to do the hack like what you're asking about, where you try to use a fixed offset, because then what happens when you start to have kind of an arbitrary number of lists that you might have an element participating in. Any other questions? Was there anything I didn't cover here? Yeah, actually, I think I've covered everything, and the last bullet actually was related to one of the questions that were asked. So the only other comment I have with respect to intrusive containers is that unfortunately in the C++ standard library, at least as of the C++ 17 standard, which is the most current version of the standard, all the container classes in the standard library are non-intrusive. So if you do want to use intrusive containers, the standard library is not very helpful. Hopefully over time this will change, but fortunately the Boost library, which is a very, very popular library for C++, it has a quite extensive list of intrusive containers that you can use, including singly linked lists, doubly linked lists, sets, multi-sets, all kinds of stuff. Anyway, so if you're in a kind of practical situation where for various reasons you want to use intrusive containers and you maybe want some of the more exotic things like maps and sets and multi-maps and so on, then there's containers that you can use from Boost that achieve this. And that basically brings us to the end of kind of the memory management section and intrusive containers and so on. And this is all that you need in order to do the next assignment. And actually, even prior to this lecture, you could have done part B of the assignment. We've already covered the material for that for a while. But the intrusive container part is in part C, I believe. Anyway, so now you can do that. Last chance for questions before we change topics here. So the next major topic in the course that I'd like to discuss is cache-efficient coding. In other words, how to write code that effectively exploits the cache for better performance. But before I can really talk about this topic in a meaningful way, I first need to give some background about caches. And even before I do that, I first need to motivate why it is that we use caches in the first place. In other words, what's the problem that we're trying to address with caches? And essentially the problem that we're trying to address is the so-called memory latency problem, which is the following. Over time, processors have continued to become faster and faster. And although there have been some speed improvements for memory, memory has not kept pace with processors. So because of this, there's a very large gap between the speed of processors and the speed of main memory. In other words, compared to the speed of a processor, main memory is, relatively speaking, very, very slow. And because of this, bottlenecks in algorithms can often arise due to memory speed, not due to the speed of the processor. In other words, memory speed becomes the bottleneck. And because of this, a very substantial amount of complexity in modern processors is actually devoted to reducing the impact of memory latency. In other words, trying to hide the fact that main memory is very, very slow. And a particularly important feature of processors for hiding memory latency is the cache, which is what we want to look at. And effective utilization of the cache is often very critical to writing high-performance code, which is why this is of interest to us here. So some of this stuff will not be new to people, but I just want to make sure everyone has sort of the same basic level of understanding, depending on which background you come from. And there's people from computer science, software engineering, other disciplines. You may know more or less of this. But anyway, just to kind of bring everyone up to the same point, the first thing I want to talk about is what's called the principle of locality. And this is a really important thing to understand if you want to understand sort of how caches make things more efficient. When you're accessing memory, memory isn't accessed in a very random sort of way. When you access particular memory locations, it's more likely that you'll access one given that you had other accesses that preceded it. And there's two different types of locality of reference. In other words, the fact that the accesses to memory are not uniform, known as temporal and spatial locality. So temporal locality refers to the fact that you tend to access the same memory over and over again. So if you've accessed a particular memory location now, there's a good chance in the very near future, you're going to access it again. And the reason for this sort of behavior is, for example, if you consider code like what's shown on this slide here. So here we have a looping variable I. So I is looping from 0 up to 10,000. each time through the loop, you're going to have to access the value of I. Basically, you're going to check the value to see if it's less than 10,000, and also you're going to need to increment I. So you have this pattern where you keep like reading and writing I, reading and writing I. It happened very frequently. So this is an example of temporal locality. The other type of locality is what's referred to as spatial locality. And what this is saying is that if you access a particular location in memory, there's a good chance that in the near future, you're going to access another memory location that's close to it. In other words, maybe just the address just before or just after, or something like this. And the reason this sort of things happens is if you look at the code example that's given here, it's not uncommon to see computations which look something kind of like this, where maybe you have an array, you're doing some sort of computation with index number 42 in the array, but this depends on like other entries which are close to it, like 43, which is just the one after 42, and like a few subsequent entries here. So this is a very kind of common pattern to see, especially when you're processing arrays, where you're maybe walking through the array and you're doing computation on a bunch of elements that are all close together in the array. So this would give you a spatial locality. And the reason why these types of locality are important to understand is that caches are designed on the premise that code has this kind of locality. It has temporal locality, spatial locality. And based on this, we're going to try to make things as efficient as possible, the hardware as efficient as possible, based on the premise that the code has good locality properties. If it doesn't, then your code is going to take a big hit in terms of performance potentially, especially if memory becomes a bottleneck in the algorithm. The memory subsystem in a computer is hierarchical in structure. So on the CPU itself, we have registers, which are effectively just a very small amount of memory that's used directly by the CPU. But sometimes we'll need to go out to main memory to actually access data. But before accessing main memory, we first go through a cache, which is a very fast memory that holds a subset of what's in main memory. So sometimes we'll be lucky and the data we'll need is in the cache, and it can be returned relatively quickly, slower than registers, but faster than main memory. But sometimes the information won't be in the cache, and then we'll need to go out to memory, basically the RAM on the computer. But sometimes the information we want might not even be in memory, because maybe we have a virtual memory subsystem and there's some paging happening and some of the data has been paged out to disk. So we might need to go to secondary storage to get information from the disk. And of course, we might also have tertiary storage as well, even larger capacity and slower devices too. And as we go from the top of this diagram to the bottom of the diagram, the amount of latency increases. In other words, the amount of delay that we have to wait in order to get the information we need increases. The capacity also increases as we go from top to bottom. So we have a relatively small number of registers. We can't store very much in the registers. We can store a little bit more in the caches, maybe on the order of megabytes. We can store more in main memory, which might be on the order of gigabytes. And then we can store even more on secondary storage, like a disk, which might be on the order of terabytes. And also, as we go from the top of the diagram to the bottom of the diagram, the cost per byte decreases. So it's much more practical to have really, really large, secondary storage like this compared to having really, really large amounts of main memory. Just a little bit of terminology. So again, a cache is just a very fast memory, relatively small. It's small because if we made it really big, then it wouldn't be able to be fast. The thing that makes it fast is the fact that it's smaller than the memory that it's being used to cache information for. A data cache is a cache that holds data, like basically accesses to variables in your program, for example. An instruction cache is used to cache the instructions, because don't forget, when you're accessing memory, there's two reasons you can access memory. One is to actually, fetch, read, and write values of variables. Another really important thing is you have to read fetch the instructions for your code that's executing. So basically, that's like a read type access. Some processors, they combine the cache for the data and the instruction together. This is what's called a unified cache. Other processors, they don't do this. Just again, a little bit more terminology. A translation look-aside buffer. This is a cache that's used for address translation. So when you're writing normal user code, like application code, on any modern system these days, they all have a virtual memory. So all the pointers that you're using, all the addresses in your code are virtual addresses. They're addresses in a virtual address space. But the only thing the hardware really knows about is physical addresses. If you try to go into access something stored in the RAM chip, you got to tell the RAM chip what physical address is the data residing at that you want to access. So there has to be something to translate the virtual addresses into physical addresses. And because this happens for every memory access that you're doing, at least for kind of user level application code, this can become a bottleneck if it's slow. So they have a cache which is specifically just for speeding up these translations, the translation from virtual to physical addresses. Anyway, so this is called a translation look-aside buffer. I guess I talked about before, there can be several levels to the cache hierarchy. So you have like a level 1, level 2, and so on cache. As the number of levels goes up, like L1, L2, L3, you're moving kind of further and further away from the processor. Things get slower and slower. And sometimes LL cache is used to denote the last level. How many levels of cache you have will depend on the particular processor you're using. These days, it's maybe not uncommon to see, well, 3 or 4 levels of cache, depending on the particular system you're using. And the basic idea with a cache is if the processor needs to read or write a location in memory, it first checks the cache. And if the data is in the cache, it just returns the data from the cache. And this is called a cache hit when the data is in the cache. If the data is not in the cache, then you encounter what's called a cache miss, in which case the system's going to have to go out to the next level in the memory hierarchy to get the data that it needs to access. The caches may be local to, like if you have a multi-core processor, because these days most processors tend to be multi-core, or at least a lot of them tend to be multi-core. If you have a multi-core processor, often you'll have some caches that are private to the core. Like for example, often the level 1 cache will be private to the core. So if you have like a quad-core processor, there's four processors actually on the, like 4 cores on the actual processor die. Then often you'll have a situation where each one of them has their own private cache, an L1 cache. Then they may have like the next level of cache might be shared between some combination of the cores. Anyway, so sometimes they may be shared, maybe they're not, maybe they're private. So you have different variations with respect to that. In order to utilize a cache, what we do is we take main memory, which is represented by this array here, and we partition it into consecutive blocks of size b bytes. So the first b bytes in memory correspond to block number 0, the next b bytes in memory correspond to block number 1, and so on down to however many blocks there are in main memory, which corresponds to m here. Similarly, the cache is also partitioned in this way. So it's partitioned into blocks of size b bytes, and b, as a matter of terminology, is referred to as either the cache line size or cache block size. They both basically mean the same thing. So in this particular case, we have n blocks in the cache. And in practice, n is going to be much less than m. In other words, the size of the cache is much smaller than the size of main memory in practice. Also, as b is typically a power of 2 as well for efficiency. On modern systems, it's not uncommon to see values for b of like 64 or 128, for example. And the basic idea with the cache is you may have some block, for example, block number 0 here in main memory. This can be stored in the cache in one of the particular blocks in the cache. So for example, in this case, block 0 just happened from main memory happens to be stored in block 0 in the cache. And here we have block 5 in main memory. It's actually being stored in block 1 in the cache. And the idea is the cache is much, much faster than main memory. So although it's small and it can't hold all of the contents of main memory, if we're lucky enough that some of the data that we want is in the cache, it can be accessed much more quickly than it would be if it was just in main memory. In terms of how caches work, there's a few things I need to talk about. The first is what's called the block placement policy. So if we have a cache, the first thing we have to figure out is how we decide if we're going to put something into the cache, where it goes, like where are the places that we can put a particular block from memory in the cache. And there's 3 basic placement policies that can be used, what are called direct map, set-associative, and fully associative. So with a direct map cache, what happens is there's only one block in the cache where a particular block from memory can be placed. So it's very restrictive. You don't have a lot of control over where things can go in the cache. And generally, the way that this is usually determined is if you have block I from memory, so the memory block is block number I, the place it goes into the cache, if the cache has n blocks in it, you just take I divided by n and take the remainder. So basically, you're using modulo arithmetic to determine in which particular block in the cache or particular memory block can be stored. And this is the only place it can be stored. There's no degree of freedom. Then we have what's called a fully associative cache, which is sort of the opposite of this. A block can be placed anywhere in the cache, so there's no restrictions at all. So these are the 2 extremes. And then somewhere in the middle, what we have is called a set-associative cache. And in this case, what we do is we say that we carve the cache up into what are called sets. And what we do is when we try to put something, we're trying to decide where something goes in the cache, we first choose the particular set that it goes into, and there's no degree of freedom here based on the number of the block that we're going to put into the cache. This will dictate a particular set that it must go in. But once we choose the set, then we can put it anywhere in the set, so that we have complete freedom of where it's placed in the set, but no freedom over the particular set it gets placed in. And typically the way that we figure out the particular set that something is going to get placed in is by using modulo arithmetic. So if you have the memory block has the number I, and S is the number of sets in the cache, we just divide I by S and take the remainder. So we're doing modular arithmetic. And just as a matter of terminology, if we have set associative cache and each set is such that there's k slots where we can put things, like k entries in the cache, we call it k-way set associative. So again, this is just a bunch of terminology that relates to block placement. Any questions about any of that? Again, for a lot of you, I suspect this is probably stuff that you've seen before, but just to make sure that everyone's sort of up to speed with this, I want to talk about it. So just a little bit more about block placement. So it turns out that really when we're talking about caches, often we just consider the case of set associatives, because essentially direct map caches and fully associative caches are just kind of special cases of set associative caches. So for example, a direct map cache is the same as a one-way set associative cache. In other words, if we have a cache with n blocks in it, we can carve this up into n sets that have only one block in each set. So effectively what you're saying is you have no control over what set something goes in, so you have no freedom here. And then once you choose the set, you don't have any choice either, because there's only one block in the set that you can choose from. So effectively, this is a direct mapped cache. At the other extreme, if we choose if n is the number of cache blocks and we choose there to be just one set, then that one set will have n cache blocks, meaning we can choose from any one of those blocks in the set. So this gives us a fully associative cache. So for this reason, in some of the subsequent slides, we often will just talk about set associative caches, because it sort of includes a special case as the other two extremes of direct mapped and fully associative caches. And maybe just an additional comment, the reason why this modular arithmetic is often used is, and in particular, often the value of m is some power of 2. So for example, the number of sets in a cache typically will be a power of 2. And the size of memory blocks as well typically will be a power of 2. Well, I shouldn't say typically, like in any real world system, I'd be surprised if it wasn't. Although I guess theoretically you could make it different, but things won't be so efficient that way. But one of the reasons why we use this modulo sort of computation here is if you're computing mod n m, where m is a power of 2, what this corresponds to is just keeping the k least significant digits of the number in binary. So like it's very efficient to do the modular arithmetic. You don't really need to do anything. You just kind of grab certain bits in the expression and you're done. Or if it's hardware, basically just using wires to read off those values. So for example, if I wanted to compute like 10, the remainder when I divide 10 by 4, if I write this in binary, 10 is just 1010 in binary, and then 4 is just 2 to the 2. So if I want to compute this, basically what I do is that since the power here is 2, I can just take the 2 least significant digits of this number, which is 10 in binary, which if I write it back in decimal is 2. So it's like really, really easy to do modular arithmetic where the thing that you're dividing by is a power of 2. Basically, you're just taking bits out of the number. So to maybe be a little bit more concrete about these various different types of caches. So for example, we have a direct map cache. So suppose that our memory looks something like this. We have blocks that are size B, and then we have our cache over here. Our cache has 8 slots in it, or there's basically 8 blocks in the cache. And then we're considering where potentially this block number 10 in memory can get put in the cache. If the cache is direct map, then basically what we do is we take 10 divided by the number of blocks in the cache, which is 8, and then take the remainder. So we're computing this quantity here, which turns out to be equal to 2. If you divide 10 by 8, take the remainder, you get a value of 2, which means that the particular block that this particular block in memory has to go into in the cache is the one with block number 2. And we have no degree of freedom. Like once you choose a particular block in memory, if you're using a direct map cache, there's only one place in the cache that block can go. So this is what we mean by direct mapped. If you go to a k-way set associative cache, like in this case, what we do, so if we have a similar story, we have like memory that's been divided up into blocks of size B, and we're trying to figure out where should the data in memory block 10 be put in the cache. With a k-way set, with a set associative cache, what we first need to do is we need to figure out what set can that block in memory be mapped to. And what we do for this is we just use, again, modular arithmetic. We take the block number, which in this case is 10. We take the number of sets in the cache, which is 4. They're numbered from 0 to 3, so there's 4 of them. In this case, when we take the remainder, we're going to get 2 when we divide 4 into 10. So what this says is that we have no choice, but the block has to be mapped to something that's in set 2. So set 2 has 2 blocks in it, so it could get mapped to either one of these, but we can't map it anywhere other than set 2. So like the set, you have no freedom in choosing the set. It comes from the block number, but once we choose the set, we can put it anywhere in that set. And then the last case is the fully associative cache case. So in this case, if we look at, again, the same sort of story here, so we have memory that's partitioned into a block sizes of B bytes each, and we're trying to figure out where block number 10 can go in the cache, and we have a cache which has 8 blocks in it. In this particular case, since it's a fully associative cache, we can choose anyone. So any block here can potentially get mapped to any block in our cache. So this gives us the most freedom, but the trade-off is in terms of the hardware and so on, it's more expensive to implement the fully associative cache, and probably all other things being equal, it'd be a little bit slower than something that wasn't fully associative. Any questions? Okay. The next thing I need to talk about is what's referred to as block identification. So that this is the issue where we're trying to access some memory location and we want to know, is the data in the cache? So how do we figure out whether something's in the cache? Previously, what we were talking about is how do we figure out where to put things in the cache? Now we want to figure out, well, if it's in the cache, how do we figure out it's there to begin with? So this is what I refer to by the block identification strategy. So in general, I'm just going to talk about set-associative caches because, again, depending on how you choose the K-way of the K-way associative cache, you can cover the case of direct map caches as well as fully associative caches. So basically what we do is we take the block number of the particular, so if we're trying to access some memory location, it's associated with a particular block in memory, which is denoted by I here. And what we can do is we can then figure out what set that particular block would get mapped into just using the formula we looked at before. We take the block number and divide by the number of sets and take the remainder. And this will tell us the particular set that block must be in. And then what we do is within that set, we look to see is the element we're looking for in any of the entries for that particular set. And in order to do this, we need to store some information for each cache entry. So typically what you'll have is a bit saying whether the entry is valid. Because when you, for example, first power up the processor, the cache doesn't have anything in it. So there needs to be a way to say that the entries in the cache are not actually valid. There's no valid data in them. So this is what this bit would be for. Then we have what's called a tag, which helps us to distinguish which particular data is in the slot in the cache if it's actually valid, and then actual data for the particular block. So on this slide, I just want to elaborate on how we make the determination of whether a particular memory address actually has data in the cache for it. So if we have a particular memory address that we're trying to access, we first decompose the memory address into a block address portion and a block offset. The block address is just the block number of the block in memory. And the block offset is the byte offset within the block of the particular data that we're trying to access. And the number of bits in this portion the number of bits in the block offset is just log base 2 of B, because this is how many bits we need to represent the block offset. And then the block address is just the remaining bits. And then the block address is further decomposed into a tag and an index. The index portion is going to be log base 2 of S, bits in size, where S is the number of sets in the cache. So effectively what the index portion of the block address determines is which set within the cache we're going to look for the particular data of interest. So essentially what we do is we use this index to determine which set to look in, and then we look in that particular set, going through all the entries that are there, checking to see if any of them have the same tag value. And if any of them do, and they also have their valid bit set so that we know the data in them is valid, then we have a cache hit and the data that we want is in that particular block in the cache. So kind of how things would work is that if we're trying to figure out whether something's in the cache, we would take the address, and from the address, we can figure out which block that particular address is associated with in memory. Then from the block, we can figure out what set that block would have to map to in the cache. And then we would go to that set, and suppose the entry for the set has K entries, so this would correspond to a K-way associative cache. And then we would check to see if the remaining bits of the address, which are stored in the tag here, match the most significant bits of the address that we're trying to look for, and also the valid bit has to be set to say that the entry is valid. And if we find such a match, then the data for that block is here, and we can just extract the data out. So this is generally how things work. And then I need to also talk about the block replacement policy. So because the caches are finite in size, eventually at some point, if you keep bringing data into the cache, eventually you're going to hit a situation where there's already all of the slots in the cache, all the blocks are filled up, and then you want to bring yet more data in. So what you're going to have to do is get rid of something that's there, evict one of the entries from the cache, and so you free up space to bring something else new in. And this is what's referred to as the block replacement policy, the particular algorithm or strategy that's used to figure out when I need to get rid of a block because I need to free up some space to put some new data there, how do I do this? And the most common approaches that are used here, or some commonly used approaches that are used, are just doing things randomly. So you just randomly pick an element to toss out so that you can use it for a new data that's being brought into the cache. Or you could throw away the element that's been least recently used. Or you might use a first in, first out kind of strategy, or something that's sort of approximately least recently used. Least recently used sort of makes sense because if you think about locality of memory, like locality of references to memory, if I'm accessing something recently, it probably has a good chance I'm going to access it again due to temporal locality, for example. If I haven't accessed some data for a long time, probably chances are I'm never going to access it. Probably I left the part of the algorithm that was accessing that area in memory, and probably I'm not going to access things again. So this is the reason why least recently used typically makes a lot of sense, but it's maybe a little bit more difficult to implement in terms of the hardware. So often what people will use is like an approximation of LRU. It's not quite least recently used, but kind of an approximation to it. And then the last thing I think I need to talk about is what's called the write policy. So what this relates to is how writes to memory are handled. And there's two aspects to the write policy. One is what do you do in the case that there's a hit, like you're writing to memory and the address you're writing is actually stored in the cache. And then what's called the cache miss policy, which is sort of the dual to this, which is what happens when you're trying to write to memory and the particular address you're writing is not in the cache, and how do we handle each of these? So in the case of writing to memory and the thing that the address you're writing to is actually in the cache, we have sort of two choices that we can make. Either we can have a write through cache or a write back cache. What a write through cache will do is if you're writing to memory and the address that you're writing is in the cache, what will happen is with a write through cache is you write to both the cache entry and you also write out to main memory. So you're going to write that value in both places. This is like, in the sense you're writing through, you're storing in the cache and proceeding and writing through and writing it out to main memory as well. The other option that we can have is what's called a write back cache. So again, this is a situation where you're writing to memory, the address you're writing to is stored in the cache. And in the case of a write back cache, what you do is you only write the value to the cache. You don't actually write the value out to main memory. And the idea is later on, when you eventually evict the entry from the cache, like at some later point, if you have to get that entry out of the cache to make room for some other data that you want to bring in, at that point, you would then write it out to memory. So you're kind of delaying as long as possible or for some long period of time, potentially, before you actually write the data out. So these are the basic write hit policies. And then write miss policies, again, this is what happens in the case where you're trying to write some address and the address you're writing to is not in the cache. So you sort of have two choices of what you can do. One, what's called a write allocate cache. What this will do is in the case that you're writing to an address, it's not in the cache, what it will do is it will first bring it into the cache and then do what it normally would do for a write hit action. A no write allocate cache, what it will do is it will write directly out to memory, but it won't actually write the data into the cache. In other words, it doesn't allocate a slot in the cache for that particular entry. And there's different combinations of these that are typically used together, but this is kind of more information that's needed for the course than what's needed for the course. So I'm just going to skip over the last couple bullets. And since we're running out of time, I think I better stop here for today.